this one. Okay. Let's get this going here. All right, got it going. Let's see. Can we see it all right with the light on? Okay. So you know that we had two types of distributions. What are the two? The basic two. Good. Yeah. Discrete continuous. Now on the let's try this one. Let's see. Okay, so on we started out with a histogram. Actually, we started out in chapter 1 and 2 with frequency graph, which all we were left with was how many tallies fell in here, if you recall. Something like that. So that our total n, our sample size, was the sum of all these things. So in this case, we had 5, 6, 7, say 8. Okay, and this was a count, an actual count. Like 1, 2, 3, depending on how many tallies it's in there. And then we did a histogram, which is basically the same thing, except we take the tallies and divide by 8. So here we had like 2/8, which is 1/4, and then we had 3/8, if you recall. And then we have 2/8 and 1/8. So and this now becomes probabilities instead of just counts, because we're dividing these tallies by that, right? And so these became histogram now, and the shape of it kind of gives us an idea of what the population is. If you remember, we were looking at the true distribution of the population. So we want to see if it's bell-like, or could be uniform, could be discrete, could be continuous. Okay, now here's what I want you to see is that when I have asks, let's suppose that this is number 4 right here, or some whatever, and I ask the probability that the random variable, notice I'm using capital X for random variable. Capital, it's not a truly random variable. I mean, it's not truly random because it's going to come up to be one of, these are the outcomes of X, and these are its probabilities. So this only has a certain amount of outcomes, right? So if I want to estimate what's less than or equal to 4, what would the probability be? From our histogram. From that graph, what would the probability of less than or equal to 4? Well, no. What's that say? 3/8 plus 2/8, right? 5/8. You should see it's the area under the curve from here on back. And if I want to know what is the probability that the random variable x is greater than 4, and what would that be? 3/8. You understand? So if you got that in mind, now we come over to the distribution, and we have this thing called discrete, and then we have continuous. Okay? In discrete, well, one of them was like a uniform distribution. Remember we had x, capital X could take on random variable. I mean, the random variable could take on a value of 1, 2, 3, 4, 5, and 6. Okay, that is the see, the reason it's not, when I say random variable, it's misleading because it's not truly random. If something was utterly random, then it'd be complete noise and there'd be no shape to the data, there'd be no structure. In engineering, we call it signal to noise ratio. And so we try to reduce the noise and pull the signal out within the noise. So this, if it's uniform, then these are the probability again, p, they all have a probability of something of 1/6. And they're spiked just like this, see? Did it just end on me? Oh. Okay. Something like that. And we see it's also uniform in that sense. But discrete doesn't have any values that it can take on between. Now, continuous, one of them shape, of course, is the famous bell curve, which goes like this. And this one comes closer and closer, but it never touches. It goes out to minus infinity. And this goes the same thing. Yet, the area under the curve is equal to 1. Guess what the area under this curve is? It's equal to 1, right? To be a proper distribution, none of these can be negative, and none of them can be over 1. Okay? So now, suppose I have the same setup now, and I ask you to find the probability, let's say this is here that I have, let's say that's 4. Something like this. Okay? So now when I ask you what is the probability that the random variable x, now it can take on any value because it's continuous, not just discrete values, you understand? So what is the probability that x is going to be less than or equal to 4? Well, guess what area that is? What would represent? Remember, these are outcomes of the random variable. Any number from minus infinity to, let's say, 4. Okay? And so if I'm asking like that, what is the probability that the random variable is less than 4? What would be the appropriate area under the curve? It shouldn't be hard from the histogram. You can't tell me a number, but what's the area? Underneath what? To where? From where? Yeah. So, again, this area under the curve will be something similar like this from our histogram. You see? It really is the area under the curve. It can be 3.5. It can be 3.75. It can be any number you want. So it's continuous because there's a y value for every x value. Okay? Now, over here on the discrete side, after we talked about these uniform distributions, we talked about, in general, when they give you something like this and they give you the probabilities of something happening, like 0.0 and 0.4, or so, something like that, and then they tell you what the random variable can take on, 2, 3, something like this. And we asked you when they do it like this, notice it's discrete, but they're giving you the probability of 0.01, 0.20, 0.40, for example. And so we got 1, let's see, we got 6, 7, and then let's say 0.30, because we have to add up to 1. Okay, this is what you're used to seeing. I mean, this is what they gave you. It's no particular distribution, but they gave you this, and the probability is the random variable. And we talked that you can see one of these would be certainly on the midterm, where we give you this table, and I want you to find the mu of that distribution. Well, that was, if you remember, was a summation of xi. Do you remember? And then we had xi, and then we had the pi, the probability of that occurring. So this was from I equals 1 to the number of categories or counts. I call them number of counts. Can't really see it. But you remember that it was just simply adding up, 1 is the outcome times its probability, right? Plus The next one is 2 times its probability, and so on, you know what I mean? That's how we calculated from that sort of table. We also calculated the deviation, right? Or the variance, which was equal to the summation of xi squared pi. Do you remember that? I equals 1 to the number of counts. And then minus mu squared, which we calculated from here. All right? Those are stuff you'll see is pretty easy to do. Just follow the formula. Every distribution has its way of calculating the mean and the variance. Are we okay with this? All right. Okay, so now in the continuous case, so we had one more. Let's talk about one more over here that's very important. It was a discrete. And you can expect a question on this particular one. It's called a binomial. Now, it turns out that the mean for that is calculated in a certain way. It's calculated times n times p, where p is the probability of success as we define it. And it can only have 2 outcomes. Kind of yes or no, right? And then we have this guy, which is the variance, or sigma squared, which is going to be equal to npq, where this is the probability of a failure. Okay? Or you can just as well do the deviation by taking the square root of npq.
So for the binomial, it's not bracket x equals x plus
Right. It's
so
not.
It's not.
No, it's np and npq, square root of. Because it's not going to be given us to us that way. So let's do one. An equation for the binomial is that the probability that the random variable x, notice that I said will take on, notice how I say this, takes on a literal value. So instead I'm going to say it takes on a particular, so I'm using lowercase x, do you see? That would be like a 4 or whatever. So this in general is going to be equal to the combination rule of n, that's the number of trials, times groups of x, times the probability of success raised to the x power times q to the n minus x.
So that whole equation is not the binomial equation, it's just.
It is a binomial.
That's what it sounds like you said it was.
I don't know what you asked then. Apparently, I thought you asked if mu was equal to x squared, something or another. And that was no. The answer was no to that. You mean the one I had earlier, like this?
No, I have it written down, that equation, and it just wrote down as the binomial equation when I just asked you, you said it wasn't.
This is not the binomial equation.
That's
Yeah, this one's a binomial. This isn't. This is how you find its average and its deviation. Okay, let's try it. Let's supposing that if you're a betting person, supposing I'm going to have 5 tosses of a fair coin. Okay, I'm going to toss it 5 times. What's the probability that I'm going to get the random variable comes up with 3 heads? Did you see? So it's either going to be a head or not a head, right? 2 outcomes. Are they independent or not independent? Well, one toss doesn't affect the next toss, does it? Somebody say yeah. So that's going to be independent. And so we're going to have n here equals 5. And the number of groups that we want succeeding is heads is going to be, we get 3 heads out of 5. What's that likelihood? What's the probability? So what I have here is a probability that the random variable x takes on a value of 3. What's this rule right here? What's that called? No, this part right here, that doesn't stand for continuous. Huh? Counting rule, which one? C should help you, yeah. It's called combination rule. That means out of 10 tries, what's the chances we get 3? All right? Okay, so let's see what it is. First of all, we have to set what our probability of success is. You could call a success a head, or you can call it tail, but I'm choosing to call it a head. So I know that the probability of any one coming is a half. Do you agree? That's the probability of success. Now Q is the probability of failure, which is simply 1 minus P. Okay? And so what's Q? It's not hard. 1 minus. Okay. Okay, so we can write that obviously as 0.5, correct? So let's try it. Let's see if we can calculate it. So this is how you calculate the average and variance of a binomial distribution. And now we have a particular example. So the way it should be is that I'm going to have, so in this case I'm going to have n, which is 5, correct? And then this is 3, and p is equal to 0.5, right? And that's going to be raised to the 3. And then times the failure, which is 0.5 again. Do you agree? But now it's going to be n minus x, so it's going to be 5 minus 3. That's the power. Okay, that's the power of the exponent. So we know that this thing is a combination rule, which is going to be n factorial, right? And so that's going to be 5 factorial, divided in parentheses 5 minus 3 factorial, divided by 3 factorial, okay? Times 0.5 raised to the 3, and then this is going to be 0.5 raised to the 2. Any questions so far? You can expect a binomial question. Okay, now, this is for what? Calculating the probability that at 3 tosses, we get 3 heads. Now, let me tell you what's really going on, why we're using this counting rule. Take a look at this. Supposing I talk like this, more theoretical, so that I have, this is the number of successes, right? The number of heads, correct? And so that's kind of looking at it like we got a head, the first toss, head on the second, head on the third, and then we have failures that we call tail, tail. Do you see? This is a possible order of these things, right? That's this, you see? That means cha-ching, cha-ching, cha-ching. We're all multiplying head, the probability of a head time, probability of a head time. You see that? But this is only one combination. How many ways can we mix up those tails among there? And that's why we have the combination rule. You understand? The combination rule tells me how many ways we can sort these tails among all these 5 choices, right? What's another choice? Obviously, we can have tail, tail, head, 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 right? And we want to list them all. So this is only half of it. That's this. Then how many ways that could be ordered is this. Okay, so 5 factorial, we know that 5 factorial, and this is 3 factorial, right? So this will only go from 5 times 4, do you agree? Because the 3 factorial will divide out. And then on top of this, we still have 2 factorial. Well, that's 20, right? And this is 2 factorial is 2 times 1, which is 2. So that means that there are 10 ways that this can happen. So the answer is, to the probability that the random variable takes on exactly 3 heads is going to be equal to, well, it's going to be equal to 10 times 0.5 raised to the 3 times 0.5 raised to the 2. And that's the answer of getting exactly 3 heads. If you use these on the right kind of gambling games, it could give you a really good what's a hint as to whether to take the bet or not, or how much to bet, and this kind of thing. I don't gamble, but that's because I know the odds. I was actually at this place for the last weekend. I didn't realize the rooms are so cheap there on the weekend. They want you to gamble, so I go there. But I was out looking, prospecting out in northern Nevada in a place called, it was called, weird name. It's a Rye Patch. You know it?
Yeah, I live 20 minutes away.
North or south? Oh, well, west or east, I should say. Because 80 is running west and east.
Well, you're coming south from that way if you're going to hit Lovelock. You hit Lovelock before that. You can't.
Yeah, I hit Lovelock first. Kind of a desolate area. But there's a Humboldt River there that's been dammed. You can cross it.
Yeah.
And up there it's called Magul Mountains or Magul Mountains. And anyway, there's
Diamond Mountain, there's Thunder Mountain.
there's Trinity. And apparently it's one of the few places where there's an alluvial earth, and so you can it's really good for detecting gold nuggets. Yeah, go with my metal detector, you know. Didn't find anything, but I found a couple bullets. But it's such a big piece of land that I'm trying to zero on it. But they found there, it's hard to find it because it's either too deep or, you know, you need a different type of mining technique, like it's in the vein.
Did you see the mountainside on the right side as you were going the right patch?
Yeah.
There's a bunch of mine shafts.
Yeah, there's mine. That's quite a mountain there. Anyway, there's so much to see. Anyway, I do the research at the University of Nevada. They have a geology library, very good library, and the maps under there is incredible. The whole section of just maps. So I spend most of my time there. And found out there's a mine here that's abandoned. It's called, is it called Hayward Hill? I don't know if any of you heard of it. It's up north of here. Had a big mine. I went to there and I asked if they had any information. Somebody wrote a dissertation on it. So I have it in my office so I can look it up and see where it might be the best place to find leftovers. Okay. That's really a probability. But I take advantage. It was $40 a night. That's like below Motel 6, but I didn't gamble. Was 20? No, this one was 40. It cost me 40. But the prices of hotels are cheap there because they're trying to get you to gamble. So I just stay there. I'm not there often though. I'm in the field or in the library. Okay. So now we're ready to finally get into this part right here. Oops. Let's see if I got that. Okay, there it is. All right. So now we're in the continuous, right? And we're going to do some right here. So we're going to be using this thing and trying to find the probability on the curve. How do we find the probability on the curve? You remember the normal curve, and we just said from 4 on down? How do we actually find that number? How do we find the area under the curve? Right, we use a table. And unfortunately the table is only what? Has what place? Well, yeah, the table that we have here is like this. So let's take a look at it. It's going to look like this. Let's see. Okay, we only have one table for the bell curve. That one table is called a standard normal. It's been standardized. Normal bell curve. Okay, this will always be centered around this sample mean equals 0. I mean always. This is the only table we have. Huh? That's right. So if I went like this and tried to show a spread, it'd be one this way and one that way. That's the only table we have. Now, if you can imagine, if I did any kind of survey at all, let's say this classroom, and I'm trying to use you as a sample to get, let's say, the average height of a student in this campus, for example. And so let's take a measurement of your histogram of your heights, okay? As a mean, and it looks like it's kind of bell curvish, so we're going to say the heights are distributed bell curvish, and they usually are. Biology tends to group up in the middle. Almost all biology. So what happens when we have this? We have a distribution of heights. Clearly, it's going to not be, it's not going to be an average of 0 height. Let's say we have average of, say, 65 inches. I'm not sure why I use inches, but let's say that we have let's say 7 for a standard deviation, okay? Let me say, yeah. So now, supposing that I pick one of you guys at random, and let's say any one of you at random, and let's say Anyway, let's go like here. Let's say this is 75 inches. Okay? Somebody say yeah. So I want to know what the probability of the random variable x is less than or equal to 75 inches. Do you understand what I'm asking? I want to know what's the probability that the area under the curve is going to be from where to where? All the way back, right? Somebody say yeah. Okay, unfortunately, we don't have a table that's over 65. It doesn't have an average of 65. We just don't have it. We don't have a variance of 7 or a deviation, right? So my question is, don't you see there's an infinite number of tables that we could have to have. If that could just vary a little bit, we need another table. This could vary a little bit, it doesn't work. So we have to find a way of modifying this guy to be underneath this, under this shape. You see that? Okay. So what I have to do then is go from here. My random variables are coming out as capital X. But when I do my transformation, all my random variables now will be coming out to Z. Because Z-scores are standardized. You understand? You will be taking a survey. Histogram tells you this population's bell curve. Then, using the bell curve, you can start to answer questions of probability as far as, like in the histogram, the area under the curve. It's called a standardized equation for solving for Z. And Z is going to be equal to any little particular x, right? Minus, we're going to have whatever the mean is, divided by S. Okay, so if you're using population things, then you'd say X minus mu divided by sigma. Okay, depends. Huh?
The top portion, what does that say?
Right here or up here? Standard normal. Standard normal bell curve, if you will. Because it's been standardized so that this guy has to be morphed over to this side. You see that? So I have to take 75 and morph it over here to see what number it would represent on the Z scale. There's my question mark. Okay? So, and now here I have a table to tell me area under the curve. So what I'm saying is that from here on back is equivalent to the modification of here on back. That's the answer to that one. But since we only have one table. Okay? So let's try it. So I'm saying that I want to get a Z-score, a particular Z-score, when X is equal to 75. Right? Then I have to subtract 65, which is mean, and I just had a deviation of 7, which I just, made it up. So you can see that this is going to be, what, 10 over 7. Correct? So 10 over 7, what do we got? Approximately 10 over 7. So that'll go once, right? And then 30. So let's see, 4. Something around like 1.4. Roughly 1.4. So I'm saying that this point here is 1.4, which is the equivalent to this guy. But this is random variable X. Now we're random variable Z's. Okay? Now, I want to know, I can answer this question by answering this question. What is the probability that the random variable Z is less than or equal to 1.4? That area will be the same as answering that question. Because we translate it over to a Z. Do you Z? That was a zoke. That was a zoke. Okay. All right. So let's do it. So let's figure it out. Let's see. We have it. Where do I have that at? Okay, I'm going to go back here. Okay. Now, when you look at the table, you can see that this is past the 50% mark, right? So all z values to the right are going to be positive. And we're looking for 1.4, correct? So I'm on the right side. So now I'm going to go 1.4. And because this now, if I was a 3, then it was 1.43, then I have to go over like 3 or 4 columns. Because up here is the 0.3, see it? 1.43? 1.4. So let's call it 1.43. So if I call it 1.43, then this 1.4, I put 1.4, but more accurately it was 1.428. So I rounded up to 1.43. So 1.43. This is the probability that the random variable would take on. This is that is the probability of, what was it, 0.96? Let me see it. 9236. 9236. What? Well, let me point out that's a good question, because, by the way, the probability of getting that's whatever this is that I set up, the probability of getting somebody, I turn the lights off, scramble you out, pick somebody, the probability that you're going to be less than 75 inches is pretty high, according to these numbers. You see that? Now, he asked a question about this, and we will be addressing that question when we talk about approximation to the binary. It turns out that under certain conditions, the binomial, see if you get this, a binomial can be calculated under the assumption of a continuous bell curve. If the sample size is big enough and some other conditions, it's easier to use the bell curve as an approximation to the binary, right? Binary or binomial is discrete, right? It has to have a bang, 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 right? Whereas continuous. So the problem here is going to be this. And it's good that you asked the question. Suppose that I have a standardized curve here. So I have, there's my bell curve, and let's say this one's standardized, or whatever. Let's say it's not standardized. Let's do the same problem. This is 75 inches, right? Now, if you notice before, when I was talking about a binomial, I asked, what is the probability that the random variable x, in our case was heads, was equal to 3? Do you see that says equal? It doesn't say less than or equal. Okay? Well, that's a problem for continuous, because if I ask you what is the probability that the random variable x takes on 75 only, well, how much area is under the curve? Under only 75. I'm asking exactly 70. I didn't say less than 75 or equals. That would be this area. What happens when I ask you? It's a trick question, because if somebody asks that kind of question on a continuous function, it's always the same answer. How much area is under the curve under 75? 1 is the whole area, so that's going to be really tough to be 1 on one spot. Huh? I can't hear you. Oh, because I got this fan blowing right in my ear. That's why I act like I'm deaf. Well, it is possible. The probability that a random comes out exactly in any continuous function is equal to 0. There is no area under a point. You understand? Kind of weird. So how do we use it as an approximation? I'll get to that. But in continuous, we can never have this equals. If you try to say it's equal to something, That's why I'm asking a question like this. What is the probability that x equals 75 less than or equal? Okay? In that case, we had 0.9236, right? So I can also ask the question is, what is the probability that the random variable x is greater than 75? Notice I don't have equals, just greater. And I hope you can see that since the whole area has to be 1, in order to get this area, I have to have equals 1 minus 0.9236. That would be the probability of getting somebody bigger, taller than 75 inches. You understand? Look at the difference. This is less than or equal, and that one's greater than. Okay? Somebody say yeah. Okay, now let's go back to the book. Okay, what is here? All right, so let's go back over that then real quickly. It's going to be, I think it's that way. Okay, now normal distribution. This is our standardized. Look here, it's 0, right? And we have a deviation of 1. Can you see it? Or is it too much light? Can we see it 1? Okay, so that's all right. Now, the one in blue has a deviation of 2, right? So it's a wider spread from the average. Yes or no? Because this is 1, right? So blue is wider because it has deviation of 2. All right. Now look what happens here. We have 0 and 2, but now this guy shift over because mu is 2 and sigma is 2. Okay, that's just how it looks under different parameters. Let's see. Okay. So here we have the mean and the standard deviation. Okay, so here we go. And right here you can see, ooh, we just did that. And, okay. All right. So we can see that plus and minus 1 deviation from mu, just 1 deviation plus and 1 deviation minus, contains 68% of all observations in a bell curve. Well, that's nice. Okay, now we have the standard normal distribution. And this is the equation that we just went over. This is how you translate x's to z's. This is your random variable x minus mu divided by the deviation. That's how you get your z. Then we find the area under the curve. So let's try it. Okay, now let's try it. Let's test it out. Look here. Now I have an interval. See these intervals? If you're on this side, they're positive z's, obviously, and you're this side, they're negative z's. Correct? So this is assuming that you've already converted these to z-scores. So if I wanted to find this area, given that the book is telling you the area from here on back, you see, so I have to take the probability. I have to take the probability of z is going to be less than or equal to z bar plus, well, that didn't go very well. This thing means plus z bar, z, okay? That's the area from here on back, of which I have to subtract from here on back. You see, I have this area, which is less than this area. But to get the interval, it's going to look like this. I want to know what is the probability that the random variable z takes on a value less than or equal to z plus and greater than or equal to z minus. That's what I'm looking for when I'm doing the interval, right? So you can think of this as 2 problems. This is 1. Calculate the probability from here on back. That would be the area under the curve from here on back all the way, right? Right? And this other guy is another problem. Just cover that up. Now I want to know the area under the curve from here on back. So really, I'm going to have to take this value of area and subtract this value of area to get my interval. Okay. Same here, same here, same here. All right, next. Let's see. Okay, now, area under the curve, 2.09. Do you see it? It's already, we already figured it out. Now, what is the probability? How would I write that? I would write it like this. What is the probability that the random variable z, right, is less than or equal to 2.09? This is how you write it, what it's saying. And you want to know what that area under the curve is. So we're going to look for, on our table, along the columns, we have, what's that? It doesn't. But given that it says z, we know that that's the case, okay? So let's see, what do I want to do now? Okay, so now I want to go here, and now I'm going to look for, along here, right, 2.0. And then over here, last column, 2.09. See it? So let's try it. So here's 2.0. Come straight across, and we have okay, 2.0 straight across is right there. You see it? That's the area from that z-score back. So all I have to do is go back. Let's go over here, and you can see that that answer is right here. And there it is. It's going to be 0.9817, or 98% chance. Okay? Very easy. The harder part is just going to be translate from x scores to z scores, from x random variable to z. So that's that done. Okay. So look, find the probability that the random variable z, because it's been standardized, is going to fall from 2.53 to 0. Well, what is the area from 0 on back? What's the area under the curve from 0 on back? What's the whole area? So guess what it is from 0 on back? Yep, half, right? 50%. Correct? Because it's symmetric. Yes or no? Okay, so we're going to have to find the area from here on back, yes? And subtract how much from that? 0.5, yes? That's right. And we don't even bother because we know that 0.5 goes from here to here. Then we look up 2.53 in the chart and we get 0.9943, and which we subtract 1/2. And that will give us this interval. You understand? Okay. Okay, that's enough of that. It says, okay, here we have, it's already been standardized, so let's go on now to application of normal distribution. It's the value minus the mean divided by the standard deviation. Okay, now, there it is. Okay, now, look at the average. What is it? Can you see it? What number? This is 5.2. You got good eyesight. And then, okay, but that's our average. Is this standardized? No. It is not standardized because it has to be over 0, right? So we're going to standardize this into a z-score. How? It's 5.4 minus its mean divided by its deviation, which is telling you 0.3. Okay, now we've standardized it over to a z-score, and our equivalent z-score is 0.067. Is that right? Mm-hmm. So let's see. Where was I? I was here. Yeah. So let's go over here. Okay, now, newspaper recycling. It turns out it's an average of 28 pounds that we have of newspaper. It says each month American households generate 28 pounds of garbage. Okay, now we're going to assume that it's approximately normal, and we have a deviation of 2. Do you see that? Okay, find the probability. This is certainly not standardized, is it? It's not over 0, and it doesn't have a deviation of 1. So I'm going to have to take this guy and standardize it. Take this guy and standardize it. So that we get the following. All right, so here it is. They average 28, right? So 27 minus 28 divided by 2 is minus 0.5. And for Z2, notice that Z1, Z2, because we have 2 scores to standardize, we have 31 minus 28, that's 1.5. Yep. So now, these are standardized Z-scores. Do you see that? So now I can find this area. This is what I'm going to find. All right, so it's going to look like this. But now it's on the standard Z random variable, and this is going to be 0, right? And what was before 27 is now what was before 31 is now 1.5. And what was before 27 is now minus 0.05. You see that? So the area of interest is from here to here. So what am I going to do? I'm going to find my probability area curve from here on back. And then I'm going to subtract from this area, from this one back. And so that I can answer the question of that the area from here on back is 0.9332. And the area from here on back is minus 0.3085. And that's the area under the z-curve, which answers the question on the x. So if I'm asking what is the probability that the random variable x takes on or is greater than or equal to, right over here is 27, and less than or equal to 31, the probability of somebody falling in that thing is, in fact, 0.6247. See it? That's this area subtracted from the other area. Okay, good. Then we can go on. Now I can get where I want to get. Let's clear that. Okay, and then we go. All right, so okay. Well, I think, is there any questions on that particular, how to do the area? Anything that goes this way forward, remember your table's going this way. You have to subtract from 1. And this is how you look at it in the table, same kind of idea. Okay. There's blood pressure. That's all easy. Okay. Here is a histogram. Actually, this is a frequency, right? See the tallies? These are the classes. This is our frequency graph. These are counts. When we divide by the summation of these, this is the n, right? This is n, which would be, let's see, this 5 and 5 is 10, and 16, 17, like 18. Yeah, 18. So there it is. Now, if I take every one of these tallies and divide by 18, I got probabilities. I have a histogram. And it looks kind of bell-like. Okay, so we'll say approximately bell curve. Gives us an idea of what the population might be. Okay, so let's go next. So, okay, so this thing here is a measure of skewness. So in this case, what they're using, this is a technique you'll need. So you'll just take the sample size minus the median divided. It gives you a sense of skewness, whether it's to the left or to the right. And if this number here is not greater than 1 or less than minus 1, so it can be concluded that it's not significantly skewed. It's a measure, a feel of how skewedness it is. So that's easy enough. Okay, this is probably the most important theorem, one of the most important theorems in probability theory. When this first came out, I had to go over the proof because to me it didn't seem self-evident. What does it mean?